Great. So if you're solving that first one for x, that first one is a linear equation in standard form. So solving it for x is 5x equals 12 plus 7y. Divide everything by 5 and you get x equals 12 plus 7y all over 5. No domain issues because 5 contains no variables. 5 will never equal 0. And number 2, you want to solve for y. So where this gets a little tricky is the fact that we have numbers and variables and a combination of variables. So what I would do is move the y to the side by itself. Therefore, I'm also going to move the number over and combine it. So that gives 3x squared. 1 minus 4 is negative 3. And then 6xy. So if you want to get y by itself, it's currently being multiplied. How do you get rid of multiplication? We divide. So we would divide everything by 6x. Now, in the case of number 2, we do end up dividing by a variable. Dividing by a variable adds to our domain. So we would have to add to this when we solve for y, but x can now no longer equal 0. If you wanted to take out a 3, everything is divisible by 3. So technically you could divide by 3, divide by 3, divide by 3, and you could have x squared minus 1 all over 2x as well. Number 3 is an example of what we call literal equations. We did literal equations back in maybe chapter 1, I think section 3. A literal equation is when we have all variables and our answer is going to have like variables with variables and no numbers. So number 3, it says a equals k squared plus b solved for k. This is a mistake I saw we make commonly, that when we tried to solve for k and k was squared, we lost half our solutions. So we would say a minus b equals k squared. But you get rid of something squared, we take a square root. When we take the square root, we create 2 solutions. The positive and negative. Because anything squared always pops out positive. That means that there are 2 possible values of k that could equal a minus b. So k is equal to plus or minus the square root of a minus b, meaning that there are 2 answers for k. So if you take the square root, you must put in plus or minus. A square root is there, we don't add it. And again, that's super important for today. It's even more important for tomorrow when we're graphing square roots, that we understand when to put a plus or minus or when not. So today we're focusing on inverses. Inverses are 2 functions that's domains and ranges are opposites of each other. So an inverse function or inverse relation is when each element of the domain becomes the range of its inverse, and the range becomes the domain of its inverse. So like an example or easy way to see that is if the original contains AB, the inverse will contain BA. So it's like saying if the original has 0, 3, the inverse has 3, 0. the original function is a, and they ask you to find a function b that represents the inverse of a, then all we would do to find set b is say that it's set a, where all points are reflections of point A. So if f and f inverse are inverses, then it is fair to say if f of a equals f of b, that is kind of like saying that f inverse b will equal f of a. So looking at another example of that, we have f of x equals x minus 4, and f inverse x equals x plus 4, represents the inverse of f. We want to evaluate f of 6, and then find f inverse of b, so it equals 6. So f of 6 equals 2. If f inverse is equal to x plus 4, then that's like saying 6 equals b plus 4. And you get b equals 2. It should make sense that b is 2 and f of 6 is 2 because the inverses are opposite points. If f of 6 is 2, then f inverse of 2 needs to be 6. They're inverses. Domains and ranges are flipped. F to the negative 1 does not mean 1 over f. It means f inverse. Because that is function notation, not exponential notation. That's one of those mistakes kids make on like an SAT before they know the proper notation. To find an inverse, please switch x and y. So if your problem is in terms of f of x, you're going to change f of x to y. Then you're going to switch x and y, and then you're going to solve for y, and then you're going to change that y to f inverse. So the steps are relatively easy. Let's actually apply them to a problem so we can understand them a little bit better. So the original function f of x is equal to 2x minus 5. So we're going to do everything for the original function, or I'm going to do everything for the original function in terms of red. So the original function, 2x minus 5, would have a y-intercept of negative 5, a slope of positive 2, and contain those points. And obviously it contains 4 points and it contains points at intercept, because a line contains every tiny minuscule point at every decimal place possible. Its inverse then, to find it, the first thing you do is change f of x to y. 2x minus 5 is equivalent to f of x equals 2x minus 5. Still in red because they're still the same function. To find the inverse, we flip x and y. So we're going to say x equals 2y minus 5. By flipping those x and y's, I have now changed to the inverse function. Solve for y. When we talk about slopes, we like to have point-slope form or slope-intercept form. So instead of keeping that as x plus 5 all over 2, we would write it as two fractions where we could see the slope of the line and the y-intercept. And again, step 4 says change that y back to function notation, and we would say that this is f inverse x equals 1/2 x plus 5x. Now, that's a rotten y-intercept in terms of graphing, because who wants to graph at 0.5? Those aren't nice points. So what I would do is try another number. So maybe I want to find f inverse of 1. Because when I plug in 1, I get 1/2 plus 5/2. Well, 1 plus 5 is 6. 6 divided by 2 is 3. So f inverse of 1 is a lot nicer to be my starting point, because x being 1 and y being 3, now taking a slope of 1/2, is much nicer. If the inverse contains the point 1, 3, what point must the original function thus contain? The inverse contains 1, 3, then the original better contain the point 3, 1. You can go to your graph and confirm 3, 1. Remember, if the inverse contains 1 point, then the original must contain the other. All graphs that are inverses of each other will be symmetric or reflect across y equals x. So this is the line y equals x. All inverses will be reflections across that line. Find the inverse of f of x equals x squared plus 1. So again, going back to my red, x squared plus 1 is a quadratic shifted up 1 unit. So it goes through 0, 1, 1, 2, 2, 5. Because again, all your perfect squares are shifted up 1. So that's like saying y equals x squared plus 1. To find its inverse, you would say x equals y squared plus 1. X minus 1. Equals y squared. To get rid of something squared, we take its square root. When we take a square root, we take plus or minus. Now, this is why we're going to learn to graph square roots officially tomorrow. What do you know about inverses? We know that their points are reflections, right? So if this is the point 0, 1, then its inverse contains the point 1, 0. if this is 2, 1, 2, the inverse contains 2, 1. Negative 1, 2 means the inverse contains 2, negative 1. So you don't actually have to know how to graph square roots yet, because you can just take all your points and invert them. You're just flipping all of the x and y's. So 2, 5 becomes 5, 2. Negative 2, 5 becomes 5, negative 2. You can always write your points down in a table if you need to, just so plotting them backwards is easier as well. Now, it's important to note the inverse of f of x is not a function because it does not pass the vertical line test. So again, we talk about like inverses and functions. These are not, the inverse is not a function because it would fail the vertical line test. It's actually why it's a plus or a minus as well. The last thing for today. Two functions are inverses of each other if and only if their compositions equal x. Two functions are inverses of each other if and only if their compositions equal x. Both compositions must equal x. If one doesn't equal x, then they're not inverses. You don't have to do the other unless you want to show like check, but you don't have to do both. So the minute one does not equal x, they are not inverses. So we have f of x equals 3x minus 3, and g of x equals 1/3 x plus 5. So if we want to determine if they are inverses, we have to do last week's lesson where we do fog and goff and determine if they equal f. So we're going to start by plugging g into f. Is x plus 12 equal to x? Is x plus 12 equal to x? No. Therefore, not inverses. Like you're done. You don't have to do goff because fog failed. Don't have to do goff because fog failed. F of x equals 2x squared minus 1, and g of x equals 1/2 x plus 1/2 to the 1/2 power. So, f of g of x equals g being plugged into x. Remember, 1/2 power is the same as the square root. The 1/2 power is the same as the square root. 0.5 is the same as 1/2. So I wrote it both ways because I want you to know that. Square root and squares cancel each other. 1/2 and 2, multiplicative inverses. They cancel each other. Again, 2 times 1/2 will become 1. So you get x plus 1 minus 1, which is x. So you're like, hey, maybe they are inverses. Then you gotta do goff. Now, because g of x is not that plus or minus, that is technically that even odd rule, the absolute value of x. So absolute value of x is not x. Therefore, not inverses. They are not inverses because you did not have the plus or the minus here. So you would only have had the top half of a square root. Your homework is next to finish the packet. It's easier to finish. So you're graphing and